Look at a sprawling solar array on a clear day, and it seems like a highly reliable power source. But when a sudden cloud cover rolls in, that generation profile drops instantly. Traditional power grids rely on the massive physical momentum of spinning mechanical turbines to ride out these sudden drops. Transitioning to a renewable microgrid strips away that heavy mechanical inertia, leaving the local system highly reactive to the environment. The immediate engineering challenge is balancing highly variable solar output with battery energy storage systems, all while forcing the alternating current to maintain a strict 50 Hz frequency. To protect these sensitive electrical balances from short circuits and surges, the network requires a robust physical safeguard. That defense comes in the form of an 11 kilovolt Gas Insulated Switchgear, or GIS. This is DIgSILENT PowerFactory. It is the simulation environment engineers use to build and test the single-line diagram of the grid. Here, we map out every generation node, busbar, and protection zone. By zooming in on the junction between the utility grid, PV array, and battery nodes, we watch the simulated active power flow, exposing exact friction points where supply struggles to meet local demand. Maintaining power during severe grid fluctuations requires precise coordination between the absolute limits of physical switchgear and the dynamic behavior of simulated electrical controls. The structural foundation of this network is a fixed-pattern 11 kilovolt gas-insulated switchgear bay. Looking at this 3D schematic, the defining feature is the double busbar configuration. Two isolated conductive layers run parallel. Operators can route energy through the primary busbar, then instantly divert flow to the secondary layer, isolating the primary bar for maintenance without dropping load. Inside the bay, the active switching is handled by fixed vacuum circuit breakers and motorized 3-position switches, physically shifting between open, closed, and earth states. Equipping these switches with motors removes the need for manual intervention on the substation floor. It enables the immediate remote operation capabilities required for an automated smart grid. If a component fails inside this sealed unit, the resulting arc flash generates immense pressure and heat. Therefore, the enclosure is built to meet a specific protection parameter, the Internal Arc Classification, or IAC-ALFR standard. A rating of 25 kiloamps for 1 second means the physical shell is engineered to contain a massive 25,000 amp internal fault for 1 full second. This provides the exact window of time required for the protection relays to trip and isolate the fault without the unit rupturing. Without this fault-tolerant physical shell containing the blast, any sophisticated electrical stabilization software running the grid is left completely vulnerable to catastrophic hardware destruction. With the physical hardware parameters verified, the DIgSILENT model shifts focus to the electrical generation mix. The model defines the solar PV arrays as voltage-controlled sources. Their output is entirely dictated by real-time solar irradiance. This chart maps the PV array's active power output. Reliant on weather, it draws a highly jagged, erratic curve. Adding wind turbines introduces a second erratic line. Instead of smoothing the curve, fluctuating wind speeds compound the grid's total bulk power volatility. A functional grid dictates that this intermittent power must be anchored by controllable thermal and mechanical assets. We introduce the steady output of synchronous microturbines and combined heat and power generators. These map as smooth, predictable curves. Through dynamic load sharing, the CHP units and microturbines are actively dispatched to cover the baseload, the exact moment the PV arrays drop out due to weather. Grid stability relies on a strict division of labor. Intermittent sources provide the raw bulk energy, while the mechanical sources provide the precise active power matching required to prevent total system collapse. But those mechanical assets have a physical limitation. They require time to spin up their heavy mechanical mass, meaning they cannot react fast enough to catch a sudden split-second drop in solar output. To bridge that immediate transient gap, the network relies on the Battery Energy Storage System, or BESS. This sequence shows the dynamic dispatch model in action. Governed by its state of charge, the battery system mirrors the sudden loss in solar generation with an instant upward spike in power injection. It carries the load while mechanical turbines slowly rise to meet demand. This immediate injection prevents the grid from experiencing localized brownouts during the crucial seconds the physical turbines need to catch up. The battery operates as the grid's high-speed shock absorber, buying the necessary milliseconds for the physical machinery to match the electrical reality. Stable grid operation also requires the management of reactive power to regulate terminal voltages. Local reactive power management is handled electrically by adjusting the excitation systems inside the synchronous microturbines and CHP generators. The mechanical counterpart to that electrical adjustment is the transformer tap changer. Inside the transformer core, a tap changer mechanically shifts to change the number of winding turns. By adjusting this internal ratio, the transformer steps voltage up or down. This forces the output waveform to smooth out and remain consistent at the load nodes despite fluctuations. Plotting total system load against total active power shows the generation curve perfectly shadowing the load demand. Adding frequency data reveals the battery's droop controls. Despite heavy load fluctuations below, the frequency is tightly clamped in a continuous oscillation strictly around the 50 Hz mark. The DIgSILENT load flow simulations validate these mechanics, proving that terminal voltages stay strictly within their safe operational limits. By tuning these tap changers, excitation voltages, and battery dispatches, a decentralized renewable microgrid successfully achieves the rigorous power quality and frequency standards of a traditional centralized power plant. The final phase of the project subjects the completed model to an ultimate stress test, an external fault cascading in from the main utility grid. When a massive electrical short circuit occurs on the high-voltage transmission lines, the resulting fault current approaches the vulnerable substation infrastructure in fractions of a second. The immediate physical defense triggers. The vacuum circuit breakers inside the GIS fire instantly, isolating the microgrid into a self-contained island mode to protect it from the surge. The electrical defense reacts just as fast. The battery storage system detects the sudden frequency shift caused by the physical isolation and injects stabilization power within milliseconds. Following the battery, the microturbines adjust their excitation voltages, taking over reactive power duties to stabilize the newly islanded network. Reviewing the post-fault metrics confirms the system logic held. We see verified checkmarks across load flow balance, transient stability, and arc fault containment. The islanding succeeded without hardware failure. True grid resilience is the direct result of meticulously validating physical isolation parameters and rapid electrical compensation systems inside simulation software, long before a single piece of copper is ever laid.